In single variable calculus, we had the first and second derivative tests to help us find the maximum and minimum of a function on an interval. You may also remember that we had to check the endpoints of the interval if the interval was finite. All of these have analogous multivariable concepts. We'll start with some formal definitions. Note that I wanted to make the third and fourth definitions to use parallel language, so I adjusted the wordage slightly from the book's presentation. I'm not going to read these definitions in full because the concept should be familiar. These ideas are all essentially the same as from single variable calculus. A local minimum is a point on the graph that is lower than all the nearby points. A local maximum is a point on the graph that is higher than all the nearby points. The absolute minimum or maximum are points on the graph that are less than or greater than all the points on the entire graph. The picture multivariable calculus is a little more complex because the nearby points are now in infinitely many directions instead of just to the left and to the right, but the basic ideas are unchanged. Critical points for single variable calculus occur where the first derivative of the function is equal to 0 or is undefined. When working with multivariable functions, we have multiple first derivatives to worry about. The key fact is that to be a critical point, they must all be 0 at the same point. Definition: a critical point of a function f is a point in the domain of f for which the partial x and partial y derivatives are both equal to 0 at that point, or where at least one of the two partial derivatives fails to exist. Notice that both equations need to be 0 at the same time. This can sometimes lead to situations where you need to solve a simultaneous system of equations. For the problems we'll encounter, these may not be linear equations, but they will be equations that can usually be solved by some type of substitution or elimination or possibly factoring. Students often forget about the possibility of a derivative not existing as a critical point. Fortunately, this usually arises out of something like division by 0, where it is clear that extra attention is required, so keep an eye out for that. Identifying critical points is the first step to identifying the extreme values of a function, but we also need to use a second derivative test. Functions of two variables are more complicated than functions of one variable, as there are 4 second derivatives, though 2 of those are usually the same for us by Clairaut's theorem. For single variable calculus, we had the concept of concavity. If the graph is concave up, the critical point is a minimum. If the graph is concave down, then the critical point is a maximum. We then have the case where the second derivative is 0, which can be a minimum, a maximum, or neither. For multivariable functions, there are more shapes. We still have something that looks like concave up and concave down, but we have to add the possibility of a saddle point, which is neither a minimum nor a maximum. But it's not quite like having the second derivative equal to 0. In that case, the second derivative test tells us nothing. But a saddle point is definitely neither a minimum nor a maximum. This is called a saddle point because it's basically the shape of a saddle, like what you would use with a horse. When you sit in a saddle, it's concave up from front to back to keep you in the middle, but it's concave down from left to right, so that your legs can go down around the sides of the horse. This mixture of being concave up in one direction and concave down in another is what makes it neither a minimum nor a maximum. Here's the statement of the second derivative test. Theorem: suppose x0, y0 is a critical point of the function f for which the derivatives are equal to 0. Let d be the quantity defined by this equation. Then there are 4 cases to consider. If d is positive and the second partial derivative with respect to x is negative, then f has a local maximum at x0, y0. If d is positive and the second partial derivative with respect to x is positive, then f has a local minimum at x0, y0. If d is less than 0, then f has a saddle point at x0, y0, and if d equals 0, the test yields no information. The quantity d is known as the discriminant of the function f. This quantity can be written as the determinant of a matrix, and this form gives a hint about how we may generalize this to higher dimensional functions. To review, in order to find the local extrema of a function, you first identify the critical points by finding where the first derivatives are 0. Then you use the second derivative test to attempt to classify them as minima, maxima, or saddles. And there's also the possibility that the second derivative test will give no result. In the next video, we're going to look at the case of a restricted domain.